with you. In order to apply that effectively, the heuristic algorithm, you can treat it like a black box with an input and an output. This is a heuristic algorithm you develop, and you want to make best use out of it. How do you go about making the best use out of the heuristic algorithm for a problem for which you care about? So the first thing you should know is you should recast your problem as an optimization problem, and you have to convert it into an objective function. If that is too difficult for you, sometimes the objective function is also written in the form of a function and is available in the internet. Okay. So in that case, you download multiple heuristic algorithms and you check which algorithm gives the best solution, and you can report that as that could also be worthy for a publication. So we in the academic circle we have a lot of pressure for publication. So there are two ways by which you can get the publication. If you have the function with you, f of x, you can download the algorithm, many algorithms, compare your function for different algorithms, which one gives the best, you choose the algorithm, and you have a valid publication for you. Okay. The second option is if you don't have the function, you can borrow the function from somewhere, uh, hopefully. And what do you need to pass it? We will now discuss what do you need to pass it to the heuristic algorithm so as to get the effective output. Okay. So you definitely need the function f of x, of course. You also need to know its dimensions, and you need to know the limits x min and x max. These are the primary requirements that you need to operate the heuristic algorithm. Yeah. If you have multiple algorithms, then you have to feed this information to multiple algorithms, get the output. The output you can expect is the global minimum location x star and the function at the global minimum location f of x star, where x star is the global minimum or the global best. In ideal conditions, the heuristic algorithm must give you the global minimum, but if it gives an accurate answer close to the global minimum, that is also okay. And you should also evaluate the value of the function at the global best that you have obtained out of the heuristic algorithm. And it is not just you run it once, you have to have a statistical comparison of multiple times you have to run. Okay. You know the f of x, you know the dimension, and you know the x min and x max, and you have five such algorithms. I'll call heuristic algorithm as HA. I have five algorithms, HA1, HA2, HA3, HA4, and HA5. So you input the same information for all the algorithms. For each of them, you supply the function that you want to optimize, the dimension, and the bounds. f of x, the dimension, and x min and x max. Each will give its own output. The first function will give h1 star, the second one will give h2 star, and so on. Each of them are locations of the individual global best. And each of them will also provide you with a global best value. So it should be f here. Okay. Now that we run 5 algorithms, HA1 or HA is a heuristic algorithm. So now that we have run the algorithm for, now that we have run the cost function or objective function over 5 different algorithms, are we done? Okay, it's not quite done. Okay, you have to show the statistical comparison that HA1 is truly, if let us say, we can give rank depending upon how the algorithms perform. Let us say this is rank number 1, this is rank number 2, this is rank number 3, this is rank number 4, and this is rank number 5. So HA2 is the best algorithm for your problem, and HA1 is the worst algorithm for your particular problem. Okay. So by running once, you cannot come to a conclusion. You need to have a statistical basis for comparing the performance of the algorithms. Okay. So you need to show that you need to run each algorithm for now they are recommending to run at least 51 times. Okay. You run 51 times, all 5 algorithms. Each algorithm has to be run for 51 times, and you get some statistical information for each of the algorithm. Okay. So HA1 you run 51 times, HA2 you run 51 times, and so on. Okay. Then you make a comparison for each of these individual algorithms. The reason why we need to take statistical comparison is that if you run once and you find that HA2 is giving superior result compared with HA1, it may be out of luck. Okay. Since you are using only random numbers, the role of luck is very high. So we need to notice that it may be due to luck that if you run once, HA2 has given a better result compared with HA5, okay, HA1. So in order to verify that HA2 is indeed the best algorithm, you have to do a statistical comparison with respect to HA1, HA3, HA4, and HA5. So how do you go about doing that? Okay. So there is a command in MATLAB called rank sum. So this is a command. It returns something known as H. Okay. So yesterday we saw 5 algorithms. So I'll call each of them. I'll give each of so each of them is generating some output. So you compare two at a time, HA1 with HA2. So you run 51 times each algorithm and generate 51 solutions. And what you do, you compare the 51 solutions of HA1 with 51 solutions of HA2. I'll do that in a program in a short while. Okay. So now I will take ACLI function, and this is my GSO MATLAB. So I want to compare two algorithms. One is GSO MATLAB, other one was a PSO algorithm that I wrote yesterday. So I'll take ACLI function. So we'll highlight ACLI function, and I will run for 51 times. The trials indicate independent trials. Okay. You run the same algorithm for 51 times and generate 51 results. So I'm asking the uh, MATLAB to run the ACLI function for 51 times. And once it does all the programming, it will store all the values in an Excel file. This command will allow 51 copies of the function, GSO algorithm, run on ACLI function, and it will be stored in GSO func num2 string dim. This is a file name, and in that particular file, all the values of GSO are stored. So while it is running, I would like to take any questions if there are any. Any questions? Okay. So once this is, yeah, the GSO is accurately locating the minima. The minima for ACLI function, in this case, for this benchmark function, is located at 0, and the function value is also 0. So by running the algorithm, we see that the ACLI function is successful in all the attempts. Okay. When I say trial equals 14, it is saying that it is a 14th trial. When it is saying trial equals 15, it is a 15th trial, and so on. So it has to run for 51 times, which will indeed be take our time. Okay. In the meantime, we will see how we can okay. What does ransom do? So ransom is a MATLAB command that compares two different outputs of two algorithms. Okay. So let us say you have two algorithms. f of x. You are essentially evaluating f of x, and let us say you have two algorithms. Okay. So the first algorithm is giving me values like this. All 51 values are located nearby each other. I'll call this as algorithm A. And the second algorithm, and that is giving results somewhere here. Which algorithm is best? This is algorithm A and this is algorithm B. The green is algorithm B for the same objective function. F of x represents increasing values of the function. F of x increases from left to right. Let us say it is a minimization problem. So you can clearly make out that algorithm A is superior over algorithm B. Is better than algorithm B. Let us consider a different scenario. You have two algorithms, algorithm A and B, and your function line. This I'll call it case 1. We have a second case, case 2. Then you have the blue algorithm, gives an output like this. So, and the green algorithm gives an output like this. So you have 4 points, out of which one of the blue algorithm is, though in statistically blue algorithm does well, for out of 3 out of 4 points, 1 point does worse, okay, compared with algorithm 2. Okay. So our algorithm 1 is generally doing better than algorithm 2, except for 1 point. Okay. So what rank sum does in this case, it will statistically separate these two algorithms and it will assign a rank for each of these points. Okay. So the blue points will get ranked like this: 1, 2, 3, 4, 5, 6, 7, 8. Okay. And if you average out the ranks for the blue, algorithm A is still superior over algorithm B. Yeah. So algorithm A is still superior over algorithm B. Yeah. Except for 1 point, which is slightly misplaced. So algorithm A is still better than algorithm B. But with less confidence. Okay. Now let us consider the third case. You want to evaluate two algorithms. And one algorithm, and both algorithms are intermingled with each other. It happens many times. You have algorithms like this: algorithm 1, algorithm A, Then you work with algorithm B. Now you see that algorithm A and B are not statistically separable. Are not statistically separable. You could not see the difference in performance between algorithm A and algorithm B. They are performing more or less the same. Okay. If you take a blue point, on an average, it is the same as the green point. Okay. So algorithm A and B are not statistically separable. So algorithm A and B are not are not different in performance. Okay. So this is how you conclude that algorithms A and B, whether one does a good job or a bad job compared with other algorithms. Yeah. Now we come back to our MATLAB screen. So we have GSO run for up to 51 times for MATLAB. We'll try to do similar thing for active function. So trials is 51. I hope this will be somewhat faster. Yeah. Any questions as this program is running?
Yes, participants.
Do you have any questions?
On the material. Okay. So let us now go ahead and compare the algorithms using rank sum command. Okay. So I have already run some programs on the Russell function. I already have done for the Ackley function also. So I'll run the Ackley function and show a demonstration for you. what I have done effectively is I have stored in an Excel file the Ackley function for 51 trials. So this has Excel file of Ackley function for 51 times. And I'm copying it into a vector. So GSO is a vector that has 51 trials of Ackley function, which is the function is given as input to GSO MATLAB program, and PSO is the Ackley function given as input to the particle sum optimization algorithm. Okay. So GSO and PSO each have 51 entries. Okay. Now you want to compare them, so you run this command rank sum GSO and PSO. Okay. The name of the this rank sum, the name of the algorithm is called Wilcoxon rank sum, okay. And it will clearly tell you which algorithm is best. Okay. If H, the value of H that we find out, if it is having the value 1, then the algorithms are separable. Okay. And which one has the lowest median, that algorithm is best compared to the other algorithms. If H turns out to be a 0, then we notice that algorithms are not separable. We have to conclude that the GSO and PSO algorithm have similar performance on Ackley function. Let us do that. Okay, I'm running the code. Okay, so we notice that the GSO and PSO have some difference in their performance, and we notice that H is 1 for this particular run. So we need to conclude that both GSO and PSO their performance is significantly different. Now let us see if we can do it for sphere function. See how things turn out to be. Yeah. For sphere function, the output H is 0. Yeah. The output H is 0. Okay. So what we see is output H is 0. So which means the PSO and GSO have no significant difference in performance. So whether you choose GSO or you choose PSO, for the sphere function, they are not performing differently. So the performance is identical for this particular function. You can also run for Rosenbrock. Let's see how things turn out. It says HS1. I'm not sure whether you can see it. Can you read it? HS1 in this case. Okay. So for Rosenbrock function, galactic swarm optimization is clearly ahead of the particle swarm optimization. Okay. So it is definitely a superior algorithm. Okay. For Rosenbrock function. Okay. You must remember, it is not one algorithm is better than other algorithm. As we have seen in the yesterday, the no free lunch theorem dictates that no algorithm can claim superiority over any other algorithm. It is only An algorithm can do better over another algorithm only for for functional case-to-case basis. In this case, for Rosenbrock function, GSO performs better than PSO. I will share the code of GSO today. Okay. We will now move on to applying to a problem. Okay. So, see, today morning, to show you the simplicity of how you can use somebody else's algorithm for your function is clearly evident. Okay. So today morning I downloaded this code just some 2 hours back. Okay. It is true that you need to know certain things about MATLAB, but not all that is required. Okay. So they have developed an algorithm called artificial rabbits optimization, and they have proven that the algorithm works for 5 different engineering tasks, namely pressure vessel design, rolling element bearing design, tension compression spring design, cantilever beam design, and gear train design. Okay. So if you look carefully, we want to test these algorithms for the same problems. Okay. We would like to use particle sum optimization over these problems. Okay. And we see how does it work. Okay. In order to do that, you need to observe certain things, that it is having a maximum iteration of 1000 and the population size is 50. So we would like to choose the same population size and the same iteration so that the comparison between two algorithms is fair. Okay. So as I said, you should know the dimension, you should know the function, and you should also know the lower and upper limits to apply this algorithm effectively. Okay. Okay. So this is our PSO code. So how do we get the information for dimension and things? You have to look into the code. They have said that, yeah, this is how ARO is an optimization algorithm. They are calling the algorithm to solve for their problem, where ARO represents artificial rabbits optimization. And let us run the program that they have given and see what is happening. It turns out they have a result. They also have a convergence curve. In modern optimization based work, a convergence curve is a necessity. Okay. So the best solution, they have a 4-dimensional problem, and the best solution for them is this. Okay. And they have the best fitness of pressure. The objective function value is 5885. Okay. I have taken that same cost function and I'm using it for PSO. We will run this program. Let us see how good our so we are having, yeah, we are running for less number of iterations. Okay. Only 50,000 times. You can increase it. We can run it again. Yeah. So we originally saw that their output value was 5885. They are nowhere near that. So for this particular function, PSO does not do that well or as compared to artificial rabbits optimization. But its performance is decent. It is around 9,000, whereas artificial rabbits was able to give around 5,800. Yeah, let us try out for another function. I'll change the index. So every index corresponds to different problem. This time also they have a convergence curve, and this time their best solution is 85,549 minus of 85,549. Let us see how our program does. Yeah, ours is also pretty close. It's actually better than artificial rabbits optimization algorithm. For the second problem, population particle swarm optimization is better than artificial rabbits algorithm. So I can also give you this modified algorithm so that you can see the comparison by yourself. So how could you get your the new algorithm to be modified according to it? So you need to look into their subroutines. Okay. They have given around 5 subroutine. Okay. You look into this subroutine, it tells you the range of the dimension, low and upper, the lower limit and the upper limit for x, and dimension is how much dimension does the problem have. In the case of 1, it has a 4-dimension problem. In the case of 2, it has around 160 dimensions. Yeah, and then D is 160. No, sorry. Yeah. Dim is around length of flow, which means it's around uh, 10. Okay, there are 10 values in the length of flow, so it has 10 dimension problem. We choose a in the third problem. It has once again 3-dimensional case, and so on. In the fourth dimension, it has only one. It's a 1-dimensional case. Pretty easy to optimize. So likewise, when any new problem or any new algorithm that you get your hands on, you just have to modify a few things at the top of the code. You have to adjust the dimensions. In this case, the dimension is given by the uh, engineering range f&x itself. You adjust the dimension from which you get the dimension. But there is one thing different from artificial rabbits algorithm compared to particle swarm optimization. If you choose the velocity minimum and velocity maximum to be x min and x max, there is a problem. Velocity minimum is not a negative number in x min, so it won't optimize properly. Yeah. The optimization will move on in one direction, that is towards the positive direction, but it will never move in the negative direction. That is a problem. So the remaining part of the code, you don't have to touch anything. Okay. It is general now it has become now it is optimizing your function, knowing the upper limits, lower limits, and you do nothing to print out. You just ask the program to print at the end what the best function is and what the location of the global best minima is. That's it. It will print it for you. Madam? Any questions the audience would like to ask? Any questions that you might want to ask?
Hello,
Tell me, sir.
Venkataraman, there is one Wilcoxon rank test that you talked about.
Ah,
Is there any other statistical test that is also used nowadays for comparison of algorithms?
so this is a median test. If you have two populations with medians, yeah, it will tell you which median. Uh, if you go by medians, the medians might not be same. Like median of algorithm A might not be same as the median of algorithm B. So rank sum test is the best test to differentiate between algorithm A and algorithm B. As far as I know, we've been using it for every paper that we submitted, and it is, and it is. I think it has not received any criticism so far.
Okay, thank you.
Okay.
Yes, participants, do you have any queries? Please ask. Yes, sir, for this command for comparison of two algorithms, that is rank sum,
Hmm.
the syntax it is as you have written on left hand side, that is V comma H.
Yeah. Tilda comma H.
So it is is it a V comma H, or in your code you have shown it is just like a sinusoidal sign?
Yeah. I'll come to that. Ah, actually, this is p value. If the p value is too low, then the population are not identical. They have to be treated as separate. You can also display the p value. If the p value is too low, then you have to treat the function as different. In this case, p happens to be 3.6 into 10 to the power minus 8. The general uh, syntax is p comma h rank sum, but if you don't want to display p, you can use the tilde command like this. Then you only your focus is only on head, not on the tilde.
Okay, sir. Thank you.
Thank you, madam. That's all I have for presenting today.
Yes, participants. Sir, can you more elaborate about the different versions of PSO and which one should be selected for getting the maximum benefit from the PSO algorithm?
Well, actually, you can also different versions. Madam, actually, in my paper, I got an opportunity to compare around five state-of-the-art PSOs. But if you look into the actual variants of PSOs, it should be around 150 or 200. Even in the published literature, that's quite huge. So I don't have a convincing answer regarding. We cannot compare all the variants of PSO. That's quite difficult. So we choose one of the latest PSOs that are available, and we have to compare with them.
Hello. Hello.
Ah, ah,
Yeah, good afternoon, sir.
good afternoon, madam.
Sir, actually, I have one question that if I have to go for the speed control of three-phase induction motor,
Okay.
so can we apply this optimization for the speed control?
Yes, madam. If it is written as a well-defined function, you can just input that function to PSO. It should give.
So, defined function means,
Madam,
hello.
tell me, madam.
Uh, we have to go for the speed control. So right now, for example, I have to for this uh, in the range of frequency where V by F ratio is same, constant. So there I have to go for the speed control. So naturally, I will take care of the torque, and there I would go for the speed control. So how can I apply this PSO? Means what should be my PSO parameters over there?
Do you have the function with you?
So torque is equal to V by F square upon under root of that formula has been there. One torque formula has been there.
Okay.
Even the current formula, that is, for example, IR dash is equal to V upon under root of RS plus RR dash whole square plus XS plus XR dash whole square.
Okay.
So that is my formula for current, and that is referred to the stator side. And torque is 3 into IR dash square into RR dash upon S upon omega ms.
Okay.
And we are keeping this V by F ratio constant. So for maximum torque, we know that V by F ratio, whatsoever may be my frequency. So for in the range from 10 hertz to 50 hertz, my ratio will almost remain constant. So maximum torque will remain constant, and I have to go for the speed control. So how can I apply this PSO over there?
you can apply. How many variables are there?
Basically, there would be speed would be there, frequency would be there.
Speed and frequency are the outputs, correct?
Yeah, speed, frequency should be my input and speed should be my output.
Okay, how many frequency components you have?
Actually, we can consider any of the frequency from 10 hertz to 50 hertz.
Okay, so there is only one frequency. There is
Yeah.
only one frequency variable, correct?
Yeah, correct. Only one.
Okay, so that would be one dimension. Okay, like
Okay.
current is you say that it also depends on the current.
Yeah, because in the formula for current, your sleep comes into picture. No, sleep is a dependent term on speed. So, naturally, our current will also vary in that
Okay.
regard. Yeah.
So, the frequency is a first level input.
Yeah, input, correct.
Okay, and frequency, depending upon the frequency, the current varies.
Current varies, speed varies, and even the torque also varies.
Okay, so there are three parameters depending on frequency.
Yeah.
Okay, which one do you want to control?
Pardon?
You want to control the speed only, or you want to have control over all three?
Actually, I want to go for speed control, keeping the torque constant.
Okay.
Yeah.
Madam, it is well, you just have to write the formula.
Okay. Yeah.
And if you have, this seems to be like a one-dimensional problem.
Huh.
So, dim is one for you.
Pardon, sir?
Dimension is one.
Right, correct.
Okay. So, what is the minimum frequency? You said minimum frequency
10 hertz.
10 hertz.
Yeah.
And maximum is, can you see my screen?
50 hertz.
50 hertz.
Yeah.
Okay. And this is your minimum and maximum.
Yeah.
Now you have to indicate the velocity.
Yeah.
Velocity minimum should be a negative number.
Okay.
It is advantageous to have symmetric velocity. Say -2 +2.
Okay.
Okay. With this, you need to write a separate function for your overall formula.
Okay.
Okay. That you have to write it as a separate subroutine.
Okay.
And the remaining part of the PSO code, you can use directly as it is.
Means this x min, x max, and dimension.
Yeah, dimension. Dimension is one. Okay. And you write the function, and let us say this is your function name. So, speed control. Yeah. You have to create a separate subroutine by name speed control.
Okay.
And you have to write it, that speed control, as a function of frequency. Any other queries from anyone?
So that function, I would be writing that subroutine, and that I would call here in this program, right?
Yes. In PSO,
And-
tell me, ma'am.
Yeah, and means like for example, right now, because I said just like in case of our when we go for this speed control using VBAP method, so we have to take care of our flux, and second one is a torque.
Okay.
Right. So means I need to consider these two things, no? Means
Okay.
is it like that? I would write separate functions for torque, then speed, then current, and whatsoever our flux, because these are all correlated to each other. So is it like that? I have to create separate subroutines and then I have to call them in the main program and then I have to run it. Will it be like
Madam,
that?
actually, the thing that you are asking is called multi-objective optimization, madam.
Okay.
If you want to control multiple parameters
Huh?
and your input dimension is the same, okay,
Okay. Huh.
that is a different type of optimization altogether. It is called multi-objective optimization.
Okay.
But in this course, whatever
Huh.
I presented
Huh.
in today's lecture,
Hmm.
it is
Single dimension.
single objective optimization. The
Okay.
function is only one dimension.
Okay.
That f of x
Hmm.
has only one unique value.
Okay.
The input could be a vector, like it could be a frequency, current, anything, but the
Huh.
output is only one dimension.
Okay. Fine.
If you are able to write your function in terms of one dimension,
Huh.
then you can utilize PSO.
Okay.
Otherwise, also you can use multi-objective PSO,
Hmm.
which you can download from the web.
Okay. How we have to do that, sir? Can you help me?
Generally, you can go to GitHub or
Okay.
MATLAB File Exchange.
Okay.
Go to MATLAB File Exchange.
Huh.
You can download from there. There are many multi-objective algorithms that are available there. From there, you
Huh.
can download.
Okay, sir. Okay. I'll definitely try.
Yeah, even if you find any paper in Google,
Huh.
and if they say that the algorithm is available, sometimes it's available in the page itself.
Okay.
If that page doesn't give you the algorithm, you can type it in Google, and if they have uploaded it in MATLAB File Exchange, that will be available.
Okay, sir. Definitely I'll try.
Yeah, generally, optimization algorithms are written only in MATLAB, generally, so far. And nowadays, people are trying in Python and all that.
Yeah, correct.
But yeah, traditionally, it's written in MATLAB, so a lot of opportunity that it is available already in as a MATLAB code for you.
Sir, just wanted to discuss. Actually, I had gone through this machine learning and all, but I feel all these things are database related. So, can we apply them in, for example, whatever I said, I have to go for the speed control. So, can we go for this machine learning? Means, do you have that information? Using Python, we say that if we have to go for, because nowadays that matplot also they are using, no? So that is using MATLAB, I think.
Yeah, but your problem has state space.
Huh.
Then you have to use reinforcement algorithm.
Okay.
That is one aspect of machine learning that you can use.
Huh.
But if the problem doesn't change with time, you can use
Huh.
heuristic algorithms to solve.
Okay. Okay.
If the problem changes with time, so you adjust the speed, but the situation becomes changed. Okay. The environment is changing, then you have to go for reinforcement algorithm. If the environment is constant, okay, let us say you are driving something, autonomous vehicle, okay, and you want to fix only the speed of the car and nothing else, then you can treat it like an objective optimization problem.
Okay.
If it goes into a different state, then it has to be a reinforcement algorithm problem.
Okay. Thank you so much, sir. I'll definitely try.
Okay, madam.
Yeah.
Anybody else would like to discuss about their work? You can try asking any question. Like Shilpa madam has asked about her work. If you have anything to discuss about your work, you are welcome to discuss. In my experience, applying optimization algorithms, students, as I have found, they seem to be more comfortable applying the algorithm rather than writing the algorithm from the scratch. So even I wouldn't recommend you to write an algorithm from the scratch. Maybe you look up literature and you see the latest algorithm, download it, and most of the time the algorithm is available already, either as a MATLAB code. Most of them write in MATLAB. I don't know why for optimization. You can directly download or request sometimes. They will give you the code. And now it has been traditionally in the modern times, even journals are asking us to upload the code. Okay. So it is mandatory now. So if you are uploading, if you are developing an optimization algorithm or anything, any algorithm based solution that you provide for a particular problem, many of the leading journals are asking us to asking all of us to upload the code. So they want to see if it is repeatable. Yeah. So what I'm trying to say is there is a lot of code available already out there. Yeah. So you might want to use it. Yeah. So plenty of code is available along with the literature. So you can exploit it and use it for your applications. Feel free to discuss anything, like any of your problem that you would like to discuss also, it's fine. The other aspects of optimization that I would know are getting too much into coding. Uh, I don't know how much I can introduce you to PSO just in 2 hours time. I wonder if it would be effective. Like, yeah. But there are certain things we covered that are definitely useful, like how to apply a given algorithm for your problem. That should be helpful to you. Like even though you did not understood the nuances of PSO, most of us, most of the students that I come across, they are far more interested in applying the algorithm rather than developing algorithm and even understanding an algorithm. Nobody cares really to understand an algorithm. They only want to know if that is useful for them or not. And that is what we saw today. If we can make best use of an algorithm by using the rank sum commands and other commands, we go ahead and use the command and see if the algorithm is suitable for your task. If that is not suitable, then you switch over to the next algorithm. Okay. So whichever one gives the best results, you go ahead with it. Actually, if you see, the no free lunch theorem is based on uh, the since all these optimization algorithms that we saw use random numbers, that is where the real problem comes. Okay. That is where one algorithm is different from the performance of another algorithm. Okay. Since all algorithms, heuristics, use random numbers, the computers that we use today are not capable of generating perfect random numbers. They only generate pseudo random numbers, meaning there is some randomness, but if you look for a long term, the randomness it is not no longer random. So the the same pattern will repeat. Though you might have some control over the command about when a random number will appear in the code, you absolutely have no control on the pseudo-random nature of the computer. That is why, on an average performance over a function, no algorithm is better than any other algorithm. And one other issue is you have to notice that you cannot have a theoretical guess that which algorithm will do better for your task. You simply have to run and see. If the algorithm does a good job or a bad job, there is absolutely no way that you can find out without running it. Okay. There is no theoretical guesses or theoretical conjecture that you can do before running the algorithm. You simply have to run and see if it works for you. That is extremely important. Okay. That is why this area of research is extremely interesting. Okay. People keep on proposing new algorithms, and their claim is, I have proposed a new algorithm. It is suitable and it works best for all the practical problems. Though it may not work for all functions or practically usable functions, if it gives superior performance, that algorithm has a lot of weightage and importance. So these are my concluding remarks. If you would like to discuss your work at a later time, also you can feel free to send me your email. Send me an email. I hope the organizers will share it with you. And with these remarks, I'll conclude. Unless you don't have any questions.
Okay, sir. Thank you.
Thank you, madam.
Thank you for your nice presentation on these two algorithms. Participants, do you want to ask any queries related with your research work? Sir is with us. You may feel free to ask related with your research work. So, as you said, sir, if you want to learn anything related with these either meta-heuristic or heuristic algorithms, first you have to make a practice to write their codes and see whether they are giving the results or not, instead of just pursuing them in terms of theoretical approach.
Yes. There is no theoretical means to identify which algorithm is suitable for your problem.
Yes, sir, that's quite true, sir. Thank you, sir. I think participants, they don't have any query, and if they are willing to ask anything, you can mail your queries to sir, and sir will definitely help us. Thank you, sir. Thank you for your nice cooperation, and you had given us insight of learning how to learn maybe the PSO algorithm or any kind of the tools for optimization techniques. So
Thank
I'm
you.
very much thankful, sir, to you, and also our resource person, another resource person, Raghunathan sir, who daily, in spite of his busy schedule, he is one of our attendees that he is daily attending our sessions, sir. So thank you also. And of course, last but not least, our all participants. Without their active participation, this STTP was not completed. Still, we are having one day ahead tomorrow. Tomorrow is again wonderful session on applications of optimization tools in power system by Professor Dr. Narayana. So, with this, I can conclude with the permission of resource person. I declare today's session is over. All the participants are requested to fill the attendance link and feedback link. And also, now we are approaching towards the valedictory function of STTP, this wonderful journey of this STTP on optimization on 18th of June, that is coming Saturday at 11:30 a.m. So I request all participants, those are willing to express their views, their suggestions, their feedback, they can put their names in chat box tomorrow. Okay, so that it will be convenient us to chalk out the complete valedictory program. So all participants, those are interested to express their views, express their suggestions, in short, feedback. So those participants are most welcome. They can put their names, as I told earlier, put your names in chat box in tomorrow's session, so we can write down their names and we can call them at the time of valedictory function. Valedictory function will be for 1 hour, that is from 11:30 to 12:30. Okay, so thank you, Dr. M.N. Venkataraman sir. Thank you, Dr. T. Raghunathan sir. Also thank you to all participants, and thank you everyone. So with this, we can end here. Thank you, sir.
Hello, तेलंग मॅडम. हॅलो हॅलो तेलंग मॅडम.
Hi, yes, sir.
मॅडम हे रेकॉर्डिंग ऑफ करून देतो आणि
हो, sir.
मीटिंग क्लोज करू मग.
Uh,